Welcome, calculus students. We are starting chapter 3. We are in the unit finally called derivatives. And this unit will actually go from 3.1 to 3.4. So I've added one more section in there. All right, this very first unit is chapter 3.1. And we're looking at this new idea of a derivative. So in the box, you will see the definition of a derivative of a function, f, at a number a, is denoted by, and that's really what's new. This terminology that we are now calling this limit a derivative, and this terminology or notation f prime of a. That's how you say that out loud, f prime of a, or the first derivative of f. And you'll notice that this formula looks a little bit familiar. This is the formula we use to calculate the slope of a tangent line at a point. So we have two versions of that slope of the tangent line. The first version is in this first box. Your book calls this definition 2. And then we also have another version, which your book called equation number 1. We are always going to use this definition number 2 because it always works. The second one does not always work in terms of it being a limit that can be evaluated algebraically. All right, so as I mentioned before, the only new thing is this, the terminology. We're calling this a derivative and this new notation. So look at example number 1. For f of x equals x squared minus 6x plus 3, the first thing we're being asked to do is find its derivative, f prime of x, at the number a. If they had asked me to find the slope of the tangent line at x equals a, I would be doing the exact same thing. So we are going to start with this notation, f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. And our function is a quadratic, so what I'm going to be doing is finding a value, an expression for f of a plus h. So I'm going to substitute a plus h into this expression up here. So we're going to have a plus h squared minus 6 times a plus h plus 3. That expression represents f of a plus h minus f of a, so I'm going to substitute a in here. So we have minus a squared minus 6a plus 3. And that is all going to be over h. So we're going to try to evaluate this limit. I know if I substitute 0 in for h, this is an undefined function, so instead I'm going to simplify this numerator. I'm going to expand out and add like terms. So we're left with a squared plus 2ah plus h squared minus 6a minus 6h plus 3 minus a squared plus 6a minus 3 all over h. And now we'll add like terms, and I'm already seeing that my a squareds are going to cancel, my 6a's are going to cancel, my 3's are going to cancel. So what I am left with is 2ah plus h squared minus 6h all over h. And we still can't substitute 0 in. However, all three of those terms in the numerator are divisible by h. So let's divide this out. So 2ah over h is 2a, h squared over h is h, 6h over h is minus 6. And now we are ready to substitute 0 in for h. So 2a plus 0 minus 6. Make sure you don't accidentally substitute 0 in for a. And that is going to leave us with the expression 2a minus 6. Now, what did I just find? I just found what I am calling the first derivative, or the derivative of the function f of x at a, or f prime of a. Okay, we'll come over here for part B. So part B says now they want us to evaluate f prime of a, or the first derivative at 3, x equals 3. So I'm going to start by bringing over that f prime of a equals 2a minus 6, and now I want to substitute a 3 in here. So 2 times 3, which is going to give me 6, minus 6, which is going to give me 0. Okay. For part C, interpret the meaning of f prime of 3. So the first thing you could say is this is the value of the derivative at x equals 3 is 0. You could also say the slope of the tangent line at x equals 3 is 0. Or you could say the instantaneous velocity at time equals 3 is 0. All right, and our very last question is find the equation of the tangent line at f of x to f of x at x equals 5. Oh, that's a different number than we started with. Let's grab a piece of paper here. I didn't leave myself a lot of room. You didn't need to name all 3 of those explanations. I was just giving you a variety of options here. Okay, so we're going to do part D down here. And we know that my f prime of a function is 2a minus 6. And I know that my f of x function from earlier is x squared minus 6x plus 3. So what they're wanting me to find is the equation of the tangent line at x equals 5. So what do I need to know in order to find an equation of a tangent line? I need a point and I need slope. So how do I find a point? We substitute the x value into the function. So I know my x value is 5. I'm going to substitute 5 in to my function. So I'm going to find f of 5. So that would be 25 minus 30 plus 3. So that would be negative 5 plus 3, which is negative 2. How do I find slope of the tangent line? Well, I would take my formula for slope, which is now the first derivative, which is f prime of a, and I substitute 5 into the derivative. 2 times 5 minus 6. 10 minus 6 is 4. So again, you substitute into this function to find the slope. You substitute into the original function to find a point. And now that I know both the point and the slope, we can just use point-slope form. So y minus negative 2 equals 4 times x minus 5. Okay. All right, so we've got one more idea to consider. At the top of the next page are 2 graphs that you should already be familiar with. It's a visual representation of that definition number 2, f of a plus h minus f of a all over h. And the second option is, the second graph is a visual illustration of equation number 1, f of x minus f of a all over x minus a. And then how you would interpret both of those. So slope of a tangent line, slope of a curve, or you could include instantaneous velocity, as we mentioned on the previous page. So in the box here, it says the derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x equals a. So an instantaneous rate of change is the same thing as an instantaneous velocity. It's also the same thing as an instantaneous slope or the slope of a tangent line. So take a look at example number 2. If a function s of t represents the distance in feet traveled by an object after t seconds, what is the meaning of the derivative? Okay, so think about a graph. This function represents distance in feet traveled by an object after t seconds. So t is your input. So this is time, and our unit is in seconds. So our y value represents distance traveled, and it is in feet. Okay, so what's the meaning of the derivative? Well, we know that the derivative is the same thing as the slope of the tangent line. So let's consider what the slope would look like in terms of its units. So it's almost easier to answer the units question first in terms of if you're being asked to interpret what the derivative is. So my slope unit, my change in y on top would be feet. My change in x unit would be seconds. So this is feet per second. And therefore, the meaning of our derivative is our velocity. So part B says, what does the statement s prime of 10 equals 40 mean? It means that when time is equal to 10 seconds, the velocity of an object is 40 feet per second. For part C, what does the statement s prime of 20 equals negative 20 mean? When time is equal to 20 seconds, so that's my input, the velocity is negative 20 feet per second, which implies this object is either falling, if it's something that we threw up in the air, or it is moving backwards, in most cases. All right, last example in chapter 3.1. The cost of producing X ounces of gold from a new gold mine is C equals F of X dollars. What is the meaning of the derivative F prime of X? What are its units? It's so much easier if you just label your input and output or your X and Y axes. So it says we're producing X ounces of gold and X is our input. So this is X and this represents ounces of gold being produced. And then our output is the cost of producing it, and that is in dollars. So for part A, what is the meaning of the derivative? Think of the derivative as the slope of the tangent line, or if we call this f prime of x, it's the instantaneous rate of change. So this is not a velocity problem, but there are an infinite number of applications that are not moving objects. So we are looking for what the change in y and the change in x represent in terms of units. So the change in y, it's cost, so that would be in dollars. The change in x is in ounces of gold. So what the derivative represents is dollars per ounce. So it's the cost to produce an ounce of gold. So it is your cost to produce an ounce of gold. Now realize that that changes depending on how many units you're producing. So that won't be a fixed number, that will change. So if you look at part B, what does the statement f prime of 800 equals 17 mean? Well, my input is the 800. What's my input? It's the ounces of gold. So that means when producing 800 ounces of gold, it cost $17 per ounce to produce the gold. So that is still a dollars per ounce, but that is the cost per ounce at the instant when we are producing 800 units. So if you were going to make the 801st unit, it would cost you $17. All right, the last part says, do you think the values of f prime of x will increase or decrease in the short term? And then what about the long term? Now, I think you could make arguments either way, depending on how well you justified it. But I'm going to go with what typically happens, which is in the short term, your rate of your cost to produce something is probably going to become more affordable for you in the short term. So I think in the short term, this is going to decrease. And the reason is, as you produce gold, you know, the amount of material you use, the gold, you're going to need the same amount to produce every ounce. The people that are actually doing the producing, you're probably going to use the same number of people to make a certain number of ounces of gold. But there are overhead costs that have nothing to do with how many ounces you're producing. It might be your building. It might be equipment that you're using. It could be overhead costs like human resources, a manager, someone that works in finance. So regardless of how many items you're producing, your overhead costs start to get split out and shared amongst these units. So if I jumped from making 800 to 810, those overhead costs are now getting shared to 10 more pieces. So in the short term, I am expecting this to decrease in terms of the dollars per ounce. Kind of like when you shop at Sam's Club or BJ's as compared to, going to Walmart or Target. You're going to get cheaper rates because they're buying in bulk because they can share their overhead costs amongst more units that are being housed in the stores. But in the long run, depending on how far out you are predicting, for example, let's say instead of producing 800 units, I predicted out to 1,800 units. Now, maybe your facility can handle 1,800 units, but what if I went to 8,000 units? Now, there might be some more costs that you have to incur because you have to invest in more equipment, you have to invest in another building. Maybe you have so many people you have to get another manager. So I'm thinking if you go so far out in the future, you actually may increase for a while just because you might have to incur some significant investment costs. And then eventually it'll start to decrease again. So you could see, costs per ounce go down and then it starts to go up when you have to invest and then it starts to go back down again. And I could understand if you have a different justification for these. It just depends on your reasoning. Okay, that is the end of 3.1. Stay tuned for our next lesson. We'll be on 3.2, the derivative as a function. Thank you so much for listening.